All right, guys, so we're going to be doing problem number 1 from the Activity 10 Day 1 sheet. We're going to do number 1, and what we're going to have to do is we're going to have to find the degree of the polynomial, the turning points, our leading coefficients, our x-intercepts, our y-intercepts, and as well as our multiplicity of our roots. Now, of course, root is the same thing as my x-intercepts or zeros. They can be used interchangeably. And then, of course, then we are going to do end behavior. In behavior, I'm going to write two different ways. One way is going to be for the regular class, and one way is going to be for my pre-AP classes. All right, so let's just dive right into this. First, right off the bat, is the degree. Well, the degree, when it's in expanded form like this, we're just going to look at the highest exponent. In this case, there's only one variable with one exponent, which is a 4. Therefore, my degree is 4. Not D, but 4. My turning points is actually my degree minus 1. So that becomes 4 minus 1. So there's actually 3 turning points in this graph. It kind of seems a little weird, but it is what it is. That's just a rule. The leading coefficient is the number that is attached, that is in front of the variable with the highest exponent. So in this case, our highest exponent is 4. The number in front of my variable x is 1. So my leading coefficient is 1. Now the x-intercepts, I only want real solutions on this example. I don't want any complex solutions or anything along those lines. So what you have to actually remember is some factoring shortcuts. There is one factoring shortcut which is called the difference of two squares, and it states that a squared minus b squared equals a plus b, a minus b. We're actually going to use this factoring shortcut to solve this problem. All right, so let's just pull this problem over here and let's start working on it. So we have x to the 4th minus 81. Well, right off the bat, I'm going to rewrite this using my exponent rules. I'm going to rewrite x to the 4th as x squared, and of course 81, I can actually write that as 9 squared. At this point, it's now in the form of the difference of two squares because I have x squared squared and 9 squared. So my a is x squared and my b is 9. So this actually factors to x squared minus 9 and x squared plus 9. Now x squared plus 9, that part's going to give us a complex root. Simply because if we end up setting it equal to 0, we're going to have to do some number squared and get a negative number, which just doesn't happen with real numbers. But x squared minus 9, if you notice, this once again is a difference of two squares because we can rewrite this as x squared minus 3 squared. And of course, we still have our x squared plus 9 just sitting over here because it's going to give us complex answers. From here, x squared minus 3 squared factors to x minus 3, x plus 3, and of course we have our x squared plus 9. Now that it's fully factored, we can actually find our x-intercepts by just simply setting this equal to 0 because all these are going to be equal to 0. That's ultimately our goal. From here, we set each factor equal to 0. We have x minus 3 equals 0, x plus 3 equals 0, and here's where it gets goofy. We have the x squared plus 9 equals 0. And like I was saying before, if we subtract 9 over here, we get x squared equals negative 9. Well, I don't know any real numbers that I could square and still get a negative answer. So this one is not going to give me a real answer. But these other two will. We add 3 and subtract 3, therefore I get x equals 3 and x equals negative 3. So for the x-intercepts, I just don't want you to say x equals negative 3 and 3. I actually want the point. So I'm going to want the point negative 3, 0 and 3, 0. Now to find my y-intercept, what I actually need to do is we're still going to use 0, but this time we're going to evaluate f of 0. That basically becomes 0 to the 4th power minus 81. When we do this, we get f of 0 equals negative 81. And I want my y-intercept as a point, so I'm going to have a point of 0, negative 81. Now the rules of multiplicity of the roots, well, really we're going to be looking right in here. And what we concern ourselves is by our exponents outside of the parentheses. So like right here is a 1. Right here is a 1. So we can actually say that the 0 at 3, the 0.30, has an odd multiplicity. Furthermore, we can also say that the point -3, 0 has an odd multiplicity. This is important as we go further on into actually graphing, because an odd multiplicity will pass through the x-axis, whereas an even multiplicity passes through, well, it touches and turns. So odd passes through, even touches and turns.